Input 4 volts, output 420 volts. Can it do 800 volts? I increase the voltage. We pushed the voltage so high, the multimeter couldn't even read it and went into protection mode.
Hey everyone, what's up? Welcome back. In this video, I'm gonna show you how to build a simple but super useful circuit. We're making a DC to DC boost converter. This cool little gadget takes a 12 volt input and seriously bumps it up, around 420 volt in our case. It uses a toroidal inductor, same donut shape coil, an NPN transistor, and just a few other common parts. This project is awesome, not just for learning some key electronics concepts, but you can actually use it in real-world projects, like powering LEDs, maybe some custom charger or other electronic devices. So definitely stick around till the end.
First thing first, let's check out the parts we'll need. Toroidal inductor. This is the heart of our circuit. Its main job is to store energy in a magnetic field. When current flows through it, energy gets stored up. When the current stops, this stored energy is released as a higher voltage spike at the output. Pretty neat, right? NPN transistor. We're using an NPN transistor like a TIP31 or a similar power transistor as our electronic switch. This guy will turn on and off rapidly, controlling the current flow to the inductor. 100 ohm resistor. This little resistor goes to the base pin transistor. It limits the current going into the base, making sure the transistor switches correctly and doesn't get damaged. 1 kilo ohm potentiometer. This lets us fine-tune the circuit. We'll use it to adjust the switching frequency, which in turn affects the output voltage. Fast recovery diode. This one's crucial. It acts like a one-way valve for electricity, preventing current from flowing backward and directing the stored energy from the inductor smoothly to the output. It must be a fast or ultra-fast diode because things happen very quickly in this circuit, and a standard diode just can't keep up. Output capacitor. This capacitor sits at the output. Its job is to smooth out the high voltage, filtering out ripples and giving us a more stable DC output. Make sure its voltage rating is high. Something around 1000 volt is a safe bet, since our output is around 420 volts. Power supply. We need an input voltage source. Anywhere between 5 to 12 volts DC will work for this design. We'll be using 4 volts today. Okay, now that we know our players, let's get building. First, we need to wind our toroidal inductor. We'll wind two separate coils of wire onto the core. One winding is our main inductor. Let's call it the primary. And the other smaller winding, or secondary, will be used to trigger or start the transistor. The number of turns on the second winding can be fewer than the primary. Make sure you wind the two coils in opposite direction relative to each other. Connect the common end of both windings together. This common point goes to your positive 12 volt supply. Connect the other end of the primary winding to the collector pin of the NPN transistor. Connect the emitter pin of the transistor to the negative terminal, or ground, of your power supply. Ground is the same point throughout the whole circuit. Connect the base pin to one side terminal of the potentiometer. Connect the middle pin of the potentiometer to the 100 ohm resistor. And connect the other end of the resistor to the other end of the secondary winding. If the circuit doesn't oscillate when you power it up later, the most likely issue is the connection to the secondary winding. Just swap the two wires of the secondary winding. Now, grab your fast diode. Connect the anode or the side usually without the band to the collector pin of the transistor. The cathode of the diode, or the side usually with the band, is our positive high voltage output. Finally, connect the high voltage output capacitor between the cathode of the diode and the negative or ground rail to smooth out the voltage. Alright, the circuit built. But how does this magic actually happen? Let's break it down. Think of the transistor as a super-fast electronic switch. That small secondary winding and the base components basically tell the transistor to turn on and off repeatedly, really fast. This is called oscillation. When the transistor turns on, current flow from the 12-volt supply through the primary winding of the inductor and through the transistor to ground. As this happens, the inductor stores energy in its magnetic field. When the transistor turns off, the path to ground is suddenly cut off. The inductor hits sudden changes in current, so its magnetic field collapses rapidly. This collapse generates a large voltage spike across the inductor, with a polarity that adds to the original input voltage. This combined high voltage, input voltage plus the inductor spike now needs somewhere to go. It can't go back through the transistor. It's off, so it flows forward through our fast diode. The diode acts like a one-way door, letting this high voltage energy pass through the charge of the output capacitor, but blocking it from flowing backward. The output capacitor stores this charge and smooths out the pulses, giving us a relatively stable high DC voltage at the output. By turning the knob on the potentiometer, we change the resistance in the base circuit. We adjust how fast the transistor switches. This change in frequency changes the output voltage. Okay, let's quickly touch on a couple more tricky details. Inductor polarity when switching and why those diodes are so important. Inductor polarity. When the transistor is on, current flows into the inductor, say from point A to the point B, where B is the collector. Point A is the more positive than B. When the transistor turns off, the inductor tries to keep current flowing in the same direction. To do this, it flips its voltage polarity dramatically. Now, point B becomes much more positive than point A. This is the high voltage spike we use. Now, why doesn't the transistor fry? That voltage spike generated when the transistor turns off can be really high and could easily destroy the transistor if it had nowhere to go or if it hit the transistor backward. Our main fast diode safely directs this energy pulse toward the output capacitor. While our main fast diode handles the boost action, adding a separate fast diode directly across the transistor's collector and emitter can provide extra protection, giving the inductive energy a safe path if needed. This diode also needs to be fast. Two important points. Any suitable NPN power transistor can work, but make sure its voltage and current rating are high enough. It needs to handle the input current flowing through the inductor and that high voltage spike when it turns off. You might need beefier transistor like a TIP31 or even switch to a MOSFET. Second point. The cheapness of the wire used for inductor matters. Thicker wire has lower resistance. Less resistance means less energy wasted as it, better efficiency, and it can handle more current. If your circuit draws less than 1 amp, maybe 0.5 mm diameter wire is okay. But if you're pulling more current, definitely go for thicker wire, like 1 mm diameter or more. It helps reduce energy loss. Now, for the fun part, let's test this piece out. I've got my 4-volt power supply connected to the input. I've hooked up my multimeter, set to DC voltage mode. Across the output capacitor, be careful with the high voltage. Alright, let's power it on. Check that out. As you can see, the output voltage has jumped way up. Now, watch this. If I slowly turn the potentiometer, you can see the output voltage changing. We can dial it in. Look, the voltage has reached around 220 volts. Pretty awesome, right? Now, let's connect a load to it. I've got this LED lamp here. Let's see inside it first. Okay, connecting it to the output. And there we go. It's lit. I'm turning up the voltage. Now, if I adjust the potentiometer again, you can see its brightness changes. This simple circuit doesn't provide a lot of current. So, if the load needs more power, you'll see the voltage drop quite a bit. But it definitely proves the concept works. So, there you have it, folks. Your very own high voltage boost converter.
I really hope this video was helpful and you understood how it's built and how it works. If you have any questions or ideas, definitely drop them in the comment section below. I love reading them. And hey, if you enjoyed this video and learned something, please give it a thumbs up and hit that subscribe button. It really helps the channel grow and let me know you want more electronic projects and tutorials like this one. Thank you so much for watching. Be safe with those high voltages. And I catch you in the next video. Bye for now.